Hi, my name is Adam Boss, and this is my third lab on black hole. So this lab had two parts. For the first lab, the purpose of the first lab was to find the mass of a black hole, and the purpose for the second lab was to determine the initial velocity of a spaceship to fly near the event horizon of a black hole and without entering the black hole or crashing into the planet. And so the ideal models for both labs included Newton's second law and their perpendicular parallel components as well as the gravitational force. And specifically by Newton's second law, I mean momentum equals, or change in momentum equals net force over time. And my results for the first lab was that the black hole had a mass of 7.41 times 10 to the 31 kilograms, and that an initial velocity of -5 times 10 to the 6 in the x direction, and the y of 9 times 10 to the 6 in the y would satisfy the motion. So the main concepts were Newton's second law, and this basically describes that the change in momentum is equal to force net times change in time, and the net force is also equal to the sum of parallel and perpendicular forces, and that parallel forces decrease velocity while perpendicular changes direction. And of course you have the gravitational force, which shows that the gravitational constant times two masses divided by their displacement times the vector explains the gravitational force. So for lab 1, the system is the star and the surroundings are the black hole. The star mass was 2 times 10 to the 30 kilogram, and the black hole is at origin with a random trajectory. And this is the code essentially that matters. Most of it was derived from the second law, and essentially you have that net force is equal to the change in momentum over change in time, and then you have p hat calculations, and you can find the parallel and perpendicular component, and basically from there, for the second part of the data, you can calculate the mass of the black hole, which is based off the gravitational law, and you find the net force itself because this is equal to the change in momentum. And by finding the change in momentum, such as here, which is equal to the net force, you can do some algebra from there to find the mass of the black hole. And then for part 2, the system is the spaceship and the surroundings of the black hole and the planet. The black hole mass is 7.41 times 10 to the 31st kilograms. Planet mass 9 times 10 to the 28 and 7 times 10 kilograms. Black hole is at the origin. And essentially here, the code just finds the net force by looking at the gravitational force on the spaceship, by the planet, and the black hole, and then summing those two, and then essentially any velocity was plugged in, and then the mass of the black hole was of course used from the one that I used in the past. And in doing so, you could, for the trial and error method, I could find a velocity, initial velocity, and its components that would allow me to pass through the event horizon without crashing into the black hole, and also not achieving the speed of light. And so one of the errors is that the black hole mass was averaged after multiple trials from the computer, and if the computer, if it had better software, better processing, it could have a more distinct calculation and a better modeling of the system. And in terms of the concepts, the difference between the net force and change in momentum is really not a difference at all. There's no difference, but the net force is determined based off, the gravitational force, which is not easily able to be determined, but momentum is simply just the change in velocity times mass, of course, but just by analyzing the change in velocity, we can see the change in momentum, which is the net force. And then to create such a velocity to enter the orbit of the black hole, the initial velocity divided by r, the Kissing circle times mass, that should equal the gravitational potential energy at all points.